Okay, good morning. On behalf of the organizing committee, let me welcome all of you to the workshop part of this program for the EIC here at ICTS, Bengaluru. So the formal inaugural session will be tomorrow because the director of the center, Professor Gopakumar, is not available today. So he said he will visit us tomorrow at 9:15 and say a few words. So we will gather here tomorrow at 9:15. But today, let me informally welcome all of you, in particular those who have come from abroad and to great trouble to get the visa. I am very happy that the visa procedure has worked out for all of you. And also all the other participants who have come from other parts of India and from Bangalore. So this is the third EIC related meeting here in India. The first one was held in IIT Bombay in January 2020. The second one was held in IIT Delhi in December 22. And this is the third one. But the new thing about this meeting is that unlike the previous two, this meeting has a school component that was conducted here last week. So we have selected about 40 students, PhD students and postdocs from different institutes in India and also abroad. And 36 of them participated in the school. And it was a very lively and interactive school. Everybody enjoyed. There were lecture sessions, there were discussion sessions, there were some interactive sessions. And that was very nice. You can find the talks. Some of the talks have already been uploaded and the lectures, video recording of the lectures will be available soon. So those of you who could not participate but interested to see it, please go check it out in the web page. And this week we are now starting the workshop part of the program. We also have a very interesting schedule of this workshop part. And apart from the regular talks, invited as well as contributed talks, there are two formal discussion sessions and I am sure plenty of informal discussion sessions. You have seen blackboards everywhere around. So whenever you see some people with whom you can clarify some doubts, just get hold of them and discuss whatever you want to clarify. So I look forward to a very interesting and fruitful workshop. I hand it over to Marco.
Okay, so let's open this first session of this workshop. So let me welcome Christina Aidala from University of Michigan. She will tell us about the studying of the longitudinal spin structure of the proton at the EIC. And okay, you have this. Let me start. No. Anyway.
Yep. Thank you. Thank you very much to the organizers for the kind invitation. It's a pleasure to be here on my third visit to India, the second time for a dedicated EIC workshop, and my first time at this beautiful campus. So the organizers specifically asked me to talk about studying the longitudinal spin structure of the proton at the EIC. I took the liberty of being just a little bit broader, EIC physics with longitudinally polarized hadron beams. So of course, this whole week is dedicated to the EIC, and for those who were here last week for the school, was also dedicated to the EIC, but just since I'm opening things here, so the Future Electron-ION Collider at Brookhaven National Lab will address three key science questions. How does a nucleon acquire mass? How does the spin of the nucleon arise from its elementary quark and gluon constituents? And what are the emergent properties of dense systems of gluons? So we'll be hearing about these throughout the week. My talk obviously focuses on the second. And after the coffee break, we'll be hearing from Elke much more about the machine and detectors. But in just a few words, the EIC will have highly polarized electron and proton beams, 70% polarization, ion beams from deuterons to heavy nuclei such as gold, lead, or uranium. The relativistic heavy ion collider has already run with gold and uranium in the past. It'll have variable EP center of mass energies ranging from 29 to 140 GeV, EP luminosity range of 10 to the 33 to 10 to the 34 per centimeter squared per second. And not only will we have polarized protons, but also polarized helium-3 beams, and there are also discussions as well for the possibility of polarized deuterons. So I was asked to speak about the protonicity structure. So using the Jaffe-Manihar spin decomposition, we can decompose the total proton spin of 1/2 into contributions from quark spin, gluon spin, and quark and gluon orbital angular momentum. And we do this at a particular hard scale, indicated by mu here. And so we're looking at the distributions as a function of parton momentum fraction x, carried by a particular parton of the total proton momentum. So what have we already learned about proton helicity structure? Well, delta sigma at a scale of 10 GeV squared is about 0.35, i.e. the total quark spin contribution to the spin of the proton is about 35%. Delta G is somewhere around 0.2, but still with much larger uncertainties than delta sigma. If improved uncertainties, improved data sensitive to the gluon spin contribution to the spin of the proton, holds with something around this, we have a significant we must have a significant contribution also from orbital angular momentum, which, however, is much more challenging to measure. So now breaking down delta sigma, so delta U, the contribution of up quarks to the total spin of the proton is positive, delta D is negative. Now the light quark C, it shows evidence of a flavor asymmetry. So the data indicate that delta U bar as a function of X is not the same as delta D bar. And a possible contribution from polarized strangeness in the proton remains highly uncertain. So just to show some extractions. So what we do to extract these polarized PDFs from data in the helicity case is really just the same process that people have used for many, many years for the unpolarized case, where you have global analyses taking into account often thousands of data points from different experiments over many years at different energies, different collision systems, lots of different processes. Put things together into a global analysis and find the best fits for your different flavor helicity distributions as a function of parton momentum fraction x that can simultaneously describe, as well as possible, all the world data that's relevant. So this is a neural network PDF polarized 1.1 fit from 2014. As I mentioned, we know well that the delta U contribution is positive, delta D is negative. And I want to point out that there are very different y-axis scales. So these are sort of nice visualizations, but if you're trying to compare uncertainty ranges on different flavored partons, they're very, very different axis scales. So delta U here is going from minus 0.1 to 0.4. Delta D is already a much smaller range, minus 0.25 to 0.15. These are like an order of magnitude smaller range for delta U bar, delta D bar. This is minus 0.06 to plus 0.04. Right, this was plus 0.4. So delta D bar is the same scale now as delta U bar. So these two you can compare directly, and you can see the green is the best fit from this particular group, neural network PDF group. And you can see that the delta U bar, delta D bar already show asymmetry. So I'll show you a plot in a minute with more data added to this. Delta S, so the strangeness contribution. Now this plot is ranging from minus 0.08, I think that says, to plus 0.03. So almost the same scale as these. And here's 0. So their fit and in PDF pole fit is slightly negative, but consistent with 0. And then delta G, this is again a very different axis range. This is from minus 1.2 to 0.8, so much larger range, the largest range of any of these plots. Even though this uncertainty band here doesn't look that much bigger than that, the scale is very, very different. And so you can see here, there's a positive range for delta G, and getting very large uncertainties as you go down to lower momentum fractions. Here is from a paper in 2020. This is now, so it's the base NNPDF polarized fit for delta U bar and delta D bar, but now reweighted with the 2013 W boson parity violating single longitudinal spin asymmetry measurement from the STAR experiment at the relativistic heavy ion collider. So this is now showing the difference. So delta U bar minus delta D bar. So if there was no C asymmetry, this would be flat at 0 across the whole X range if they were the same distributions. And you can see the original NNPDF pole fit is the larger green band. And you can see that with the reweighting from this W boson data, which is sensitive to the flavor separated anti-quark distribution, light anti-quark distributions in longitudinally polarized protons, we both have a reduction in the uncertainty, and the central value gets a bit farther from 0. So the W boson data from STAR provided further evidence for a light light C helicity asymmetry. Here's another group, JAM. This is JAM 15 results. These are JAM 15 results. They have some more recent results that they published, which have been a bit controversial, so I chose to show these. This is for delta U, delta D, delta S, and delta G. Again, pay attention to the different scales. So this is going up to 0.5. This is going down to 0.14. Delta G is a smaller scale than the last fit plot I showed. This is only minus 0.1 to 0.2. In delta S here, their extraction shows something significantly negative with relatively small uncertainties in this extraction from 2015. You can see it's compared to a range of other distributions, and you can see in particular for the strangeness and to some extent for the gluon, there are big ranges in the different extraction methods, the different groups doing these. It's great to have different groups doing these, using slightly different techniques, working with mostly the same data. And so it gives us a better, let's say, a better handle on the systematic uncertainties on the extractions. So here are, this is DSSV14 extraction with Monte Carlo sampling now. So it's sort of an update using the same data set. This is a 2019 paper based on the original fits from 2014. Again, delta U, delta D, relatively small uncertainties on those. Here's the delta U bar, their delta D bar. You can see their delta U bar best fit. It's this darker line here. It actually is negative first and has a node and goes slightly positive within a small axis range, minus 0.04 to 0.04. But they showed a node in this extraction. Delta D bar is basically all negative in their extraction, and delta S is very small, slightly, well, just a tiny bit positive maybe, but consistent with 0 in their extraction. And here's their delta G, and you can see significantly non-zero and positive in this relatively moderate to high X range, and then very uncertain below X of 0.01. So the latest DSSV extraction of light C in gluon, these are DSSV preliminary results, is how they were labeled in the Rick Cold QCD white paper that came out on the archive in early 2023, about a year ago. So this now, so in the light blue, we have the DSSV14 extraction. And I had mentioned this node here in delta U bar that was in that extraction. The darker blue bands and the new central value with the dark blue curve are adding RIC data through 2022, what was available through 2022. And you can see, so again, this included additional W boson data from RIC, the parity violating single longitudinal spin asymmetry. And you can see that it increased the light quark C differences. So it brought their best fit from the earlier data through 2014. It was down here with this node and slightly negative at relatively large X. And the new, including the new data, and this is now a new global fit, not just a reweight, brings it significantly up and makes the difference between delta U bar and delta D bar in this relatively large, moderate to large X range even stronger. And you can see how similarly the delta D bar also got a little bit farther from 0, more negative. Here's the delta G improvement. So this now includes jet, dijet, and pion, double longitudinal spin asymmetry data from RIC that has improved uncertainties on the gluon distribution. Still looks relatively similar central value that they got. But you can see how the uncertainties have decreased from the light blue band to the slightly darker blue band, including this new data from RIC. So could contributions from low momentum gluons be large? Is something that people are discussing now. So this is also from a plot from the Rick Cold QCD white paper posted a year ago. And it includes, again, RIC data released as of 2022. So this is only for delta G now. So this is the delta G truncated first moment from X values of 0.05 to 1. So gluons carrying 5% to 100% of the total proton momentum on the horizontal axis here, and which ranges. Now we have different, very different axis scales for the horizontal and vertical on the same plot. On the vertical axis here, we have another truncated moment from 0.001 to 0.05. So 0.001 is about the lowest X value that the RIC data reach at 500 GeV with the 500 GeV running there. The axis range here is much larger, from like minus 0.8 to 1.4 or so. Well, DSSV-08 is the largest. This was an earlier extraction by the same group. DSSV-14 is this light blue that I've been talking about. And then adding to that, the RIC data that came out through 2022. You can see how much, well, you can see how delta G truncated first moment between 0.05 and 1 is relatively small. So something like 0.18 to 0.26 or so, the width of the dark blue area. And you can see the improvement from the width of the light blue area before that data was added. And then the uncertainty here is still from 0 to 0.5 on contributions from 0.001 to 0.05. And then of course below that, we just don't have data. Yeah, constraints for 0.001 to 0.05 have been improved, but there's still large uncertainties, right? 0 to 0.5. So if that range is 0.5, we'll be carrying 50% of the total gluon spin. And yeah, it's unconstrained below x of 10 to the minus 3. So the EIC will be complementary with ongoing and previous polarized experiments. So this is a XQ squared kinematic coverage plot, and we have a lot of fixed target data, fixed target DIS data down here. The dark filled blue points are relativistic heavy ion collider data, so polarized proton-protons rather than deep inelastic lepton-nucleon scattering. These points at a fixed Q squared value here are the RIC-W program, so they're all at the W mass squared. And you can see the red range here. It's a little bit hard to see. This is one of the lower Y range for root S of 20 GeV for the EIC, and then this black range. So here's the lower one to the upper one there for the top EIC energy root S of 140 GeV. So the EIC at high energy will be critical to reach down to x to the minus 4 down in this region here. There's Elka and collaborators had a lot of nice fits looking at the impact of EIC pseudo data to improve gluon and quark helicity distributions. So here are the gluon and quark singlet helicity distributions. So that the light blue is again the DSSV-14. So this is delta G as a function of x. And now this down here this is 10 to the minus 5x. Remember, we only have data from something like 10 to the minus 3 or so, and better, smaller uncertainty data from 10 to the minus 2. Again, you can see how the DSSV-14 error bars are blowing up on delta G, already below x of 10 to the minus 2. So with EIC inclusive DIS measurements at root S of 45 GeV, you can see how much the uncertainty improves on delta G. Delta G as a function of x from this light blue band going off the plot. Now the plot is minus 0.1 to 0.15. And then with EIC inclusive DIS over the full energy range we expect to run, so 45, the energies considered for the study, 45 GeV and 140 GeV, the top energy, you get this dark blue band. So very nice constraints down to 10 to the minus 4, 10 to the minus 5. Here's the singlet, a similar plot showing how uncertainties are reduced already a lot with the 45 GeV lower energy data. This is through the constraints on delta G. The strongest constraints actually are through scaling violations of the polarized structure function G1. So this is inclusive deep inelastic scattering measurements. You just measure the scattered electron off of your longitudinally polarized proton beam. So what's shown here is dG1, d log q squared as a function of q squared in bins of x. And the lowest x bin here is 8 times 10 to the minus 5. And there's only 1 point, only 2 points for the next at 1 times 10 to the minus 4. Having only a few q squared points at these low x values is because you're in this corner here in the kinematic coverage. So your low x is corresponding to relatively low q squared. And the highest x point that's shown in this particular plot is 8 times 10 to the minus 2. There's also a study done, I'll close with different collaborators now, on this paper from 2020, accessing gluon helicity through double longitudinal asymmetry for dye jet production at the EIC. So this now is EIC pseudodata for dye jets from both QCD Compton scattering and photon gluon fusion. It's really a complementary measurement to the more powerful inclusive polarized DIS structure function scalings of G1. So this is dye jet mass, ALL, the double longitudinal spin asymmetry as a function of dye jet mass for two different Q squared regions, 1 to 10 GeV squared and 100 to 500. So the paper from 2 slides ago, the same one as this, also had the impact of projected EIC inclusive DIS data on the total quark helicity distributions, so U plus delta U plus delta U bar, delta D plus delta D bar, and delta S plus delta S bar, with adding inclusive DIS data from the EIC at 45 GeV and also going up to the 140 GeV. Again, the light blue is the DSSV, and the darker colors are the 45 and 45 to 140 GeV. This is now including helium-3 data, so improving, again, the total quark helicity distributions, delta U plus delta U bar, delta D plus delta D bar, delta S plus delta S bar. But now, inclusive DIS on longitudinally polarized helium-3, so you have an effective polarized neutron, so you have more down quarks present, and so you get your flavor separation using, combining your polarized proton and your polarized helium-3 data. You can also do flavor separation to get your delta U bar, delta D bar, and delta S bar through semi-inclusive deep inelastic scattering measurements of identified hadrons. So kaons, K plus, K minus, gives you sensitivity in particular to the strange quark, for example. Again, note different y-axis scales with respect now to plots on the previous slide. So this is minus 0.03 to 0.04, the same across all 3 here. This is starting from, all these are starting from the DSSV-14, as this paper came out in 2020, before the 2023 white paper had updated preliminary fits. This has the node in delta U bar from DSSV-14. Right, the current treatment that's in this paper assumes delta S equals delta S bar. We would have obviously charge separation of our K plus and K minus, so we would have potentially separate sensitivity to separate delta S and delta S bar. So there's been some real low X contributions in orbital angular momentum. I've been talking a lot about quark and gluon spin contributions. That's what's been easiest to measure, although of course we still have large uncertainties on gluons and strangeness and more to learn about the C. This now is a plot of 1/2 minus the truncated first moment of the spin contribution from both the gluons and the quark singlet. So 10 to the minus 3 to 1. So basically this is where we have data, 1/2 minus the truncated first moment where we have data. And the DSSV-14 data set actually, the central values in here, but there's actually a relatively wide range of that 1/2, the total proton spin, minus what we've measured so far, ranging from minus 0.5 to almost 0.5. With the EIC, on this, the vertical axis is the truncated first moment from 10 to the minus 6 to 10 to the minus 3. So very small x, gluons and quarks, the total quark singlet contribution as well. So we can see how much these, the distributions or the uncertainties on these truncated first moments, or the difference from the total spin of the proton on this axis, shrink with EIC inclusive DIS data at just 45 GeV, center of mass energy, or 45 and 140 for this smaller ellipse here. So if the L plots here are basically saying if we manage to constrain very well the total contribution to the proton spin from gluon spin as well as the total quark spin, then the rest has to be orbital angular momentum. So this L equals 0, it'll cross 0, 0. It should cross, so if there's nothing, so 1/2 minus the truncated moment from where we already have data, if that's equal to 0, then I'm not going to have any contribution. I don't need any contributions from lower x, and I don't need any contributions from orbital angular momentum. So this is showing where these different contributions from orbital angular momentum would be if we had different contributions for spin of gluons and quarks from 10 to the minus 3 to 1 and lower x down to 10 to the minus 6. So yeah, people have been starting to think a little bit more about possible contributions to delta G from low x, below 10 to the minus 3 or so. There's been a relatively recent series of quite a few papers, so a whole string of papers from 2016 onward from Yuri Kovshigov and collaborators, a number of different collaborators on small x helicity evolution. This has led to new phenomenology considering possible large spin contributions from x less than 10 to the minus 4 or so. And there's now JAM small x fit that has looked at, or JAM small x fit that uses this small x helicity evolution, and currently the data just don't constrain below about 10 to the minus 3. So you can see in that JAM small x extraction of G1P, this is the inclusive polarized structure function. You have this wide green uncertainty band below x of 10 to the minus 3. Here they show how much better this would be constrained down to x of 10 to the minus 5 from the EIC, making three different assumptions on the replicas for G1. So assuming things are larger, sort of in the middle, or the negative, the lowest, that their contributions that they're considering. There's also been rapid theoretical progress, and just thinking of theoretical progress in this area of small x helicity contributions. There's also been rapid PDFs. I won't be talking about that here, but we'll have a talk later in the week, more than one perhaps, about lattice QCD. So thinking a bit more about polarized helium-3 at the EIC. So of course, polarized helium-3 can serve as a proxy for polarized neutrons. I already showed the improvements in flavor separation from inclusive DIS measurements on helium-3 taken in conjunction with measurements on the proton. And of course, we do this by using isospin to map the flavor-dependent distributions in the proton to those in the neutron. So every U gets mapped to a D, every U bar to a D bar, and vice versa. As we reach the era of high-precision polarized data with the advent of the EIC, and might we be sensitive to differences in proton and neutron structure that break this isospin correspondence? The mass difference between the proton is only like 0.1%, so this is not a big effect. But when I think more about quark dynamics, and this is something that I started thinking about more in the context of transverse momentum dependent distributions, where you're really focused on dynamics rather than these collinear helicity distributions. So quark dynamics in protons versus neutrons, and in the context of helicity structure, the interplay between helicity distributions and orbital angular momentum. So if I just think, in my scale inside my hadron, I have some limit where I have approximately asymptotically, I can picture approximately asymptotically free quarks inside. If I just think of my valence structure being different, QCD doesn't couple differently to up and down, and it's not the flavor that matters per se, but the electric charge is different. So having 2 plus 2/3 charges and 1 minus a third charge versus the neutron having the valence quark composition of 2 minus a third charge particles and 2 and 1 plus 2/3. Is this going to lead to different dynamics potentially, just the electromagnetic interactions that could lead to breaking, an interesting breaking between this isospin correspondence? And is that something, once the EIC is running with both polarized proton and polarized helium-3 beams, we might be able to explore? Of course, we'd have to, we're not looking at a free polarized neutron beam. So we have to consider how nuclear binding affects helicity distributions in the nucleons. If we want to, we'd have to disentangle that. If we were interested in what I'm trying to explore, what I was just talking about on the previous slide, we'd have to try to understand what those effects would be. We could also be interested in understanding it in its own right. We already know from a lot of data on unpolarized nuclei that their unpolarized PDFs are significantly modified with different modification at different x value ranges. Yeah, how does polarization affect the modification of nuclear PDFs with respect to the nucleon in different X ranges? And I didn't find any literature about polarized anti-shadowing or polarized shadowing for the different regions of nuclear modification of unpolarized PDFs. There's a little bit of literature on polarized EMC effect. There's a discussion in the EIC Yellow Report, which came out in 2021. There's another citation looking at this from 2022. Of course, if you really wanted to explore the polarized EMC effect, and for those who aren't familiar with it, I'll say a bit more about it in the next few slides. You'd want a range of nuclei with a lot of different atomic mass values. So, okay, polarized beams with nuclei heavier than helium-3 would be extremely challenging at the EIC. Not at all clear that that would be possible, but are there prospects for eventual fixed target measurements with polarized heavier nuclei that we could make complementary measurements to explore this more? So for those who might not be familiar with the nuclear modification of PDFs, it's just unpolarized collinear PDFs. So here are ratios of inclusive structure function F2 for electron nucleus collisions with respect to electron deuteron collisions. Deuteron as opposed to a proton, just because the isospin matches a bit better to the heavier nuclei, the ratio of 1:1 for neutrons to protons. And as a function of X, you can see, well, first of all, the ratio isn't 1, and it's got this particular shape as you go to different ranges in X. So the very high, as X approaches 1, I think that's well understood as Fermi motion in nuclei, leading to this. This range here is what gets known as the EMC effect between about X of 0.3 and 0.8, where you have this downward slope and then it starts rising. There's this region where there seems to be an excess above 1, right below that, X of 0.1 to 0.3, so still relatively large X, sort of valence-like. Anti-shadowing, this was called. And then there's a suppression at low X called shadowing. So here again are, this was a paper that looked at, this is carbon to deuterium, beryllium to deuterium, helium-4 to deuterium, and other nuclei, and fit these slopes, basically, in this EMC region. So fit the slope of the ratios for X between 0.3 and 0.7 compared across nuclei, and saw if they made a plot of basically this, you can think of this as the slope as a function of average nuclear density. So a number of the points seem to line up kind of nicely, deuterium, helium-3, helium-4, carbon-12, but beryllium-9 was an outlier. And this is one that I found, I think this is neat, it's one of the few points where I see already a relatively clear connection between people working in nuclear physics at the level of quarks and gluons, like myself, and people working in low energy nuclear structure who think of helium-4, who think of beryllium-9 like this, which I would never have thought to think of until I saw this plot a number of years ago now, that the beryllium-9 structure is basically 2 alpha particles and an extra neutron, sort of a halo neutron farther out. And so the average nuclear density for beryllium-9 is very different from the local nuclear density, whereas the average and the local density in helium-4 are quite consistent. So when they scaled with local nuclear density, this beryllium-9 point fell in line nicely with the others. And so, okay, the takeaway here is that helium-3, so the only polarized nuclear beam that we know, or the heaviest polarized nuclear beam that we plan to have at the EIC is helium-3. Of course, the large effects are for the heavier nuclei, but there is a small but non-zero effect measured for unpolarized helium-3, so I think it could definitely be interesting to explore. And of course, we'll be having, I mean, it's just inclusive, we'll be taking the data anyway, because it's inclusive DIS. Possibility of polarized deuteron beams at the EIC. So polarized deuteron beams at the EIC are much more challenging than polarized helium-3, but would offer a number of interesting opportunities. You'd have reduced nuclear effects compared to helium-3 if you want to disentangle what's going on with nuclear binding versus what it would be like if you had, say, a free neutron. Spectator tagging would allow measurement on a nearly free neutron. You can also potentially do it with helium-3 as well, but it's very easy to think about. I'll show you a picture on the next slide of spectator tagging for deuterons. Deuterons also would allow us to study tensor polarization, so they're spin-1 systems. I'm not going to say more about that here, but there's a discussion in the EIC report on this. And in general, much less work has been done on spin 1 systems than spin 1/2 systems. There's starting to be a bit more interest. There are 2 experiments planned at JLab, for example, with tensor polarized deuterium targets. And there'll be a talk on Friday, I think, on spin 1 systems here as well. I'm not selected anymore. Got it. Yeah, so your spectator tagging with a deuteron beam. So basically, if you measure the spectator proton, so in events where you interact with the neutron, you have a deuteron beam, you interact with the neutron, the proton basically carries on to the far forward region. If you have instrumentation there, you measure the presence of the proton, including its PT. This will give you sensitivity to the neutron virtuality. So this is the spin asymmetry measured as a function of neutron virtuality, which you're getting based on your measurement of the far forward spectator proton PT. If you do this as a function of this neutron virtuality, you can't get all the way down to the free neutron, obviously, but you can get a good sense of what kind of trends there might be and extrapolate a relatively modest amount at the end there. So just a quick speculation, I've got an undergrad who's been thinking about nuclear fusion and talking to me a lot lately. So it got me wondering if knowing the unpolarized or polarized partonic structure of light nuclei could someday be helpful to improve the efficiency of fusion reactions, which are getting a lot more attention in the energy sector and the research sector now with commercial involvement starting in. Looking quickly to see if people are interested in polarization for deuteron polarization for fusion. I don't know the literature at all, but I was able to quickly find a few things, including this one, multiphoton fusion of light nuclei in intense laser fields. And they hadn't looked at spin yet, but they said future investigations should contemplate the utilization of a more realistic optical potential featuring a rigid core and nuclear spin. So I just want to, in my last few minutes, or last minute or so here, I just wanted to quickly flash a few other topics. So I was told not to talk about TMDs, was my instruction, but some of them have longitudinally polarized beams, right? So if you if you take into account the transverse momentum of your partons inside your neutron, then you open up to spin momentum correlations. So the unpolarized and these spin-spin correlations survive integration over the partonic transverse momentum. If you don't integrate out that partonic transverse momentum, you get 5 other explicit spin momentum correlations, or in some cases, spin-spin momentum correlations. So this Wormgear function is one that would involve a longitudinally polarized proton beam. You can also look at the transverse momentum dependence of just your standard helicity spin-spin correlation as well. So there's very little data on H1L perp. It would be it's a func TMD PDF that's sensitive to transversely polarized quarks in a longitudinally polarized proton. And you can't integrate over your transverse momentum. So it's a spin-spin momentum correlation. There's some data from Hermes and class. So far, no evidence for non-zero asymmetry, but higher precision data is expected from class 12. And we would have access to that. One slide quickly mentioning the G-spin sum rule, generalized parton distributions, and orbital angular momentum. There will be talks later this week on GPDs. So the G-spin decomposition is different from the Jaffe-Manihar one. So it's only in terms of the total angular momentum of the gluon, not separating out orbital and spin. And the delta sigma is the same as Jaffe-Manihar, but the LQ is a different definition. So matter and gauge degrees of freedom can't be unambiguously separated in a gauge theory, so you get these different definitions of your orbital angular momentum. And the moment, so since the helicity, the total spin of the proton, the remainder, once we account for the spin of the gluons and the spin of the protons, the moments of some generalized parton distributions for longitudinally polarized protons can be related to quark orbital angular momentum, and GPDs are measurable via exclusive processes, for example, deeply virtual Compton scattering to access quarks. So one slide here on just generalized transverse momentum dependent distributions, GTMDs. So the formulation of generalized transverse momentum dependent distributions encompasses both the Jaffe-Manihar and G decompositions. So here are a few references for that. There was a recent paper relating the G and Jaffe-Manihar orbital angular momentum, so that the L for the quarks, orbital angular momentum for the quarks, using a GTMD approach on the lattice. There have also been recent proposals to access gluon orbital angular momentum experimentally at the EIC via single and double spin asymmetry in diffractive dijet production. And then this is using the framework of GTMDs. All right, so this brings me to my summary. The EIC will open up a great wealth of new opportunities to study the longitudinal spin structure of the proton and the neutron, as well as many other spin-dependent and unpolarized observables. And the more we learn in the upcoming years from theoretical developments, as well as existing and near-term data, the more fully we will be able to exploit the EIC's powerful and unique capabilities once it turns on. Thank you.
Thank you very much. Very nice talk. Questions? Raju? There should be some scatter micro. One is up
there. Can you hear me?
Yeah.
Can you go to slide 23 or 24, something like that? Yes, this one. So, sorry?
No, go ahead.
I've talked to you before about it. So my claim is that this work completely ignores the physics of the chiral anomaly at small x, and that has profound consequences. Okay, and that's the elephant in the room at small x in G1. So my claim is two things: factorization is broken for G1 at small x, and this physics is very sensitive to the physics of the chiral anomaly. And what I'm saying is not so bizarre. This was the same thing was said by Veneziano and collaborators in '89. Okay, so I keep saying this, and that's totally ignored. I mean, so we have two papers with Andrei Tarasov, which we have kind of made this point. The consequence, if we are right, is profound in the sense that this will be first evidence for Faldorn transitions in nature from measurements of G1 at the EIC. Okay, so I hope at least my experimental friends will not just ignore this, but also mention this as a possibility along with others. I mean, especially since you mentioned this work by Kochego and collaborators.
Yeah, okay, yes, we have discussed it before, and that is a fair comment that I can certainly, I'm not a technical expert on this work or your work on this subject, so I don't have a position one way or another, but I can certainly add, reference to your work in the future.
Yeah, I mean, I think it's not a question of reference. I mean, it's really that, what is the role of the chiral anomaly? I mean, that's a very interesting, profound question.
It isn't.
And to me, and I think to most people in physics, this would be far more interesting than saying, what is the delta G content? Okay? Because, I mean, that has, the chiral anomaly has consequences for many other areas of, particle physics and just in general. So for example, Faldorn transitions, right? Faldorn transitions tell you something about the early universe. So the existence of Faldorn transitions in QCD would be something highly non-trivial. So, and I think all these analyses assume factorization, and actually that's very problematic at small x in G1.
The EIC should be a great place to explore factorization breaking at low x.
But it's very hard if you don't believe in the factorization paradigm to look at the data. And because much of the analyses assume factorization, they kind of internalize that. So to really go and look for evidence that factorization is broken is very hard, okay? And the basis of the way things are done currently. So what I'm arguing for is a different way of thinking and also accepting the possibility that factorization may be broken for polarized DIS. So anyway.
Just to be on the safe side, is there any work that tried to quantify this factorization breaking? Because you know that also in the TMD, if you look at hadron collisions, you have proofs of counterexamples of breaking factorizations, but nobody has ever computed how big is this effect. So in other words, how large is your mistake if you assume factorization?
Right. So for example, I mean, if you assume factorization, right, again, it's a question of factorization means different things to different people, okay? What I mean is that G1 is not controlled by a leading twist operator, okay? It depends on the topological susceptibility. That's a big effect, Okay, and in fact, the physics is really very similar to the physics of axions, actually. So it's really the physics of the eta prime. So it's the same underlying physics that gives eta prime its mass. That's a very big effect. So, so it's explicitly broken. It's not given by a leading twist operator. And then it's a quantitative question of seeing whether you can extract the quenching of G1 because of these effects relative to some other effects. So I think it'd be good to, I mean, you know, they may be right? But at least one should have, I mean, there are claims of how this would behave at small x. And
no, I'm thinking that since we are going to low x and, the phase space coverage of EIC at low x means low q. Then at low q, of course, you should start worrying about higher twists.
So my statement about factorization breaking is not specific to small x. I mean, of course, because I mean, so for example, Veneziano's result is that delta sigma is proportional to the square root of the topological slope of the topological susceptibility. Okay, that's work from 1989, by the way. Okay, and no one has said that this is wrong. And so, and the topological susceptibility is not a twist-2 operator, right? It's a higher dimensional operator. And people can measure it on the lattice and have done so. So Kefe and friends have done that also.
To what extent are you making, I mean, so we're going to be measuring the inclusive DIS cross-section or reduced cross-section, right? I mean, we're going to measure it. We don't, the cross-sections, we're not interpreting it in any kind of picture. We're measuring the cross-section. So,
absolutely, absolutely.
So
that's what we need.
People are free to interpret it with whatever theoretical apparatus
absolutely,
they would like.
That's what we need. Yeah.
Okay.
Thank you. You have it. You should switch it on.
Yeah. Yeah, right. Yeah, thank you for Raju's comment. We have a lot of discussion before, but I am a lattice practitioner. We have a paper on the relation between quark spin and anomalous word identity. We use overlap. That's the fermion formulation, which has exact higher symmetry. That's why you can calculate that. And we showed that anomalous word identity at the finite moment, you have to get the Forman for the off-forward limit, moment transfer. They are satisfied exact within error bars. So there's no anomaly. And the anomaly GG tilde, E dot B contribution, this is a derivative A mu, right? Give you GG tilde. If you calculate A directly, that GG tilde contribution, as far as we know, contributes to the disconnect insertion, like delta S is coming from it, so that is coming through that. So there's no contradiction there, but we can understand the spin crisis in a way that anomaly contributes is reflected at disconnect insertion calculations.
Thanks for the comment.
Another question.
You have,
Can I look at around page 20 or so for the neutron helium-3. So if this is a helium-3 is supposed to measure the neutron, right? So should the design of be different from that of the proton? Is the sign? Oh, the sign is.
These are for the proton using also helium-3 data. So these would be the and Elka can correct me if I'm wrong. These should be the distributions in the proton incorporating those. Right.
You take the helium-3 because, of course, it constrains the d-quark better. So this is not the distribution in the neutron. It is a global fit to proton and helium-3 data, what we show here.
But shouldn't you expect that to be a different sign for the
only if I look only to the neutron. But if I do a combined fit of proton and helium-3, then I can kind of define them. And the helium-3 is mainly used to get the d-quark distributions. Because that ones you constrain better with neutron because it's 2D and 1U, and so that's why.
I just wonder, when you look at helium-3, did you switch the sign somehow?
Yeah, but if you look only to helium-3, it is not only helium-3, it is everything. It's a combined fit to all the data.
Got it. Thank you.
More questions? Up there.
On the slide 18, probably where you were talking about dijets. Right, so on the right plot, when I see on uncertainty on the PDFs, this is probably from the 100 replicas of the NNPDF you have computed this, right?
Sorry, could you repeat that?
The uncertainty you have computed, the hashed green ones, this is
Yes.
probably from the NNPDF replicas you have taken an average.
It is, my understanding is it's from the NNPDF replicas, as it's
Right.
basically written on the plot. And
Yeah.
yeah, Elka's a co-author on
Yeah,
this
yeah.
work.
So my question is, how do you see around 40 GeV-ish, the uncertainty shrinks almost to zero, and whereas 20-ish and 60-ish, it's significant.
It's an artifact of the replicas and how many replicas you have available.
So this is nothing to do with
No,
any physics?
no,
Okay.
no, nothing. Zero, utterly zero.
It's the beyond the standard model particle that we found through dye-jet math.
One question up there.
For the asymmetry in the light C quarks, so we have a difference for polarized to unpolarized case, right? So do we have an understanding for this? So for polarized, we expect U bar to be more, and for unpolarized, it's D bar, which is more, right?
So you're asking if we have an understanding of where the polarized, the asymmetry in the D bar U bar comes from, like the mechanism. We definitely don't have a definitive answer for that, and I actually don't know what people are talking about so much for the polarized. And people have different ideas about the unpolarized a light quark C asymmetry that aren't conclusive yet either. Like there's no mechanism that explains all the data satisfactorily at the moment for the unpolarized light C asymmetry, and I'm not aware of the satisfactory explanation for the light quark holistic asymmetry either. But if somebody in the audience knows more, they should feel free to comment.
Seems not.
Yeah.
Last question.
Okay. So in the fits that you showed in the beginning of your talk, what are the constraints that you use actually, other than just fitting it to the data? Do you put some rule constraints like G1 has to be like this, or F and D that one uses for first moments? Do you use all of them, or actually for these fits? Or?
So I'm not directly involved myself in any of these fits. The different groups make slightly different choices, which is I think that's healthy for the field that we have different groups that making slightly different choices. Elke, you want to comment? Yes. So there are, an assumption on the strange S equal delta S equal delta S bar. People use, I think all the groups assume that right now. If you want to say something specific, go ahead.
So the only complete world data fit to all polarized data, PP and DIS, is DSSV. Everybody else uses a smaller set.
Choice of data set.
So NNPDF uses inclusive data and the W data and some chat data, but no CDs and things. GEM doesn't use the digit data, so that's why some things come out very weird. So the only complete fit is DSSV for all the data. There is still an assumption of the Bjorken sum rule in the fit, so which actually forces, especially the strangeness, to have some of this behavior down there, and also forces the quarks to go to a certain delta sigma to go to a certain value, because we don't have enough data to constrain this. What else was your question?
Yeah, that's one question. Actually, related question, you have never mentioned whether these fits are LO fit or NLO fit or NNLO fit. Usually in unpolarized distributions.
They are all next to leading order fits, and actually says next to leading order now as well by Werner Vogelsang and Daniel de Florian. They have calculated something in even a higher order.
But they don't have a full extraction with that
I
yet,
had
right?
one more, actually. Okay. So in semi-inclusive DIS that you mentioned,
Yeah.
You said at EIC, this is going to improve the extraction of delta G. But semi-inclusive DIS means you need to include fragmentation effects. And
You need to include what effect?
Semi-inclusive will have fragmentation contributions, right?
Right.
And that's going to make it difficult for you to extract delta G, right? Because fragmentation is not well understood.
Well, we'll have a lot more data between now and then, also from the EIC, from VEL2, from PP at the I'm on LHCb, so we're doing identified hadron measurements there as well right now, and going through the next 10 years until the advent of the EIC. I mean, one of the reasons for in the other 2020 paper that Elke was a co-author on, of showing also the helium-3 contributions, was to address the fact that the helium-3 inclusive DIS, you get some more flavor separation without having to worry at all about uncertainties on the fragmentation functions like you do in CITES. I mean, they're complementary probes, but we will also know a lot more about the fragmentation functions 10 years from now than we do now.
Yeah, one thing with EIC is also we will have so much CITES data that we can do a combined fit of PDFs and fragmentation functions, which is absolutely critical. And we have a paper on that as well, where we show that this works very well, because at low X or at high X or at low C, the uncertainty comes either from fragmentation or PDFs. And so you have to do a combined fit.
Okay, we are running out of time, so let's thanks Christine again, and thank you for the questions.